Going on to Chapter 10, this deals with counting methods. And again, our whole course is based around this concept of mathematical ideas and seeing how different aspects of math fits into our life. And of course, you're not always interested in everything, but some things will always be affecting your life that relate to math. So, counting. The first topic that we skip is counting by systematic listing. I'm going to show you just some quick examples of this that we will then bring into the topic we're actually going to do, which is 10.2, using the fundamental counting principle. We're also going to cover topic 3 using permutations and combinations. Now, it may look daunting, but there'll be some recipes that you follow, and of course you can use your notes. So from the previous slide, you saw someone at a fast food place or a restaurant of some type, and the owner is wondering how many different kinds of combinations could customers get. Well, if you didn't order any extras, there would be only the one way that you're going to order. But there are a number of extras. For instance, if there are 8 extras, then that would affect something. And then they go through a list of combining the numbers. So this leads into counting, finding the number of objects that you could possibly get. A simple example of this would be in coins. You have a head on one side and a tail on the other. So if you just had one coin, you have 2 possibilities, a head and a tail. And then later in our course, we're going to deal with what we call probability, but not quite yet. We're still in the counting stage. But then if you had 2 coins and you're going to flip them, how many different possibilities? Well, 2 heads, 2 tails, and then 1 a head, 1 a tail, and 1 a tail, 1 a head. So there'd be 4 possibilities. Now, as we continue in this first section, just a light review. You can make charts to check things out. One of the famous charts is rolling a pair of dice. Now, a single one is called a die. 2 would be the dice. And there's a chart of the various combinations. So with 2 dice, each with 6 sides, how many can you get altogether? Well, if you were to count them, you'd see there are 36 possible results. Now, I wanted to show you some of the other diagrams, and of course you have your textbook, but if you had 3 digits, a 1, a 2, and a 3, how many different possible combinations could you have? Well, you could do a tree diagram like they're showing here and then count them. But as you see, this would get kind of tedious as the numbers get big. Another that's often a challenge is how many triangles are in this figure? And again, you could write them out or you could count them. So as we start our section that's in our curriculum, using the fundamental counting principles, we're going to more closely tie this into the mathematics of it, and let's look at some of the definitions here. Uniformity and the fundamental counting principle. And it does review what was done in section 1. We obtained complete lists of all possible results for various tasks. However, if the total number of possibilities is all we need to know, then the actual listing is usually unnecessary and often difficult or tedious to obtain. So, if we're looking at show all the possible non-repeating 3-digit numbers using only the digits 1, 2, and 3, then a tree diagram, as you list them here, and it indicates if they're not repeating the possibilities, there's only 6. Now, it is significant that we think of what we skipped over in section 1 to what we see here. Here, when we're talking about uniform in the sense that a given part of the task can be done in the same way no matter which choices were selected for previous parts. For instance, if you chose the 1, then, and as long as they're not repeating, you can select a 2 or 3. If you chose the 2, you still have 2 choices. You can select a 1 or a 3. And if you chose the 3, then you still have the choice of 1 or 2. Now, what we had done earlier, though, in the case where repetitions were allowed, you select one number, but then you have 3 choices. It could be a 1, 2, or 3. So again, depending upon what qualifiers they're giving you in the example, whether repetitions are allowed or not. So we end up with the uniformity criterion for multi-part task. Again, some of the vocabulary. A multiple part task is said to satisfy the uniformity criterion if the number of choices for any particular part is the same no matter which choices were selected for the previous part. That's where uniformity comes in. So we get, and a key word here is non-uniformity, in the case where they do set requirements and say no 2 adjacent switches could both be off. So they're putting qualifiers on there. So that would be not uniformity, but non-uniformity. Which leads us to not having to make these charts and trees. We're going to follow what is called the fundamental counting principle, which states when you have k task, that would be the number of tasks, and it satisfies uniformity criterion if the first part can be done in this many ways, the second part can be done in this many ways, so on through the number of items in the listing, that's the letter K, then the total number of ways to complete the task, and this is the formula, is given by the following product. Now remember, product is a result of multiplication. So, n sub 1, this might be a 5, this might be a 4, this might be a 3, or whatever, and we'll see this as we move through this section. This is what is the formula of fundamental counting principle. Now you saw it illustrated with all those diagrams. Now we're just going to use the math. And what they're suggesting here is if you have a formula, use it. Practice it. So as we look at example 1, counting the 2-digit numbers. How many 2-digit numbers are there in our number system, which is a base 10? And you may or may not realize this, but these are the symbols that we use in our base 10 number system. A 0, and then these symbols. And then we combine them through an orderly sequence to get our counting numbers. Well, keep in mind that 40 is a 2-digit number, but the 0, 4 is not a 2-digit number. So, our task here is to select or construct a 2-digit number. So as we think of it, if we're going to have a 2-digit number, how many of these symbols can we use? Now they're saying for the first spot, you can't use all of them. There would be 10 here, but you can't use the 0 as the first digit. So the number of ways to select the first digit, there's only 9 of them. But now, when you get the number of ways to select the second digit, there are 10 possibilities. So according to our rule, n sub 1 times n sub 2, it's a funny looking n here, let's make it a little bit better. You have 9 for the first selection, 10 for the second selection. So the number of different ways you could combine this is 90. So the answer to this first one is 90. And again, much better than having to make all those possibilities through a tree chart and then count them. We now have a mathematical formula to help us. Now in example 2, as we look at it, we see that find the number of 2-digit numbers that do not contain a repeated digit. So you can't have 2. So here the task is you select a first digit. Now, can you use a 0 of the 10 digits or the 10 symbols that we had there? And the answer is no. So how many do you have to select in the beginning? 9. Now, how many are available for the second digit? Well, you can't repeat the one you just used. So out of the 10 symbols, but now you can use a 0, there are still 9 remaining. So for this formula with a restriction, and you don't want repeats, 9 times 9 is 81. Remember before we had 90, so there are less because you're not going to allow 22 and 11 and 33. You're eliminating repeats. Now here, this was described again in a section that we're not covering, But if we look at what is here, you have a club, N, and it has these particular members, let's say. And as we look at their names, we see that this is a male, this is a male, this is a female. I'm using my genetic symbols from biology. This is a male, and then this is a female. So we have 3 males and 2 females. But the restriction they're saying is, let's read it carefully, you want to elect a president and a secretary if no one may hold more than one office. So if you're in one office, you can't hold the other. And the secretary must be a man. Now, they're saying as you read through here, the uniformity criterion is not met, and our attempt to apply fundamental counting principle has failed. But then they go on to say not all is lost. You can kind of switch it around a little bit and say, well, how many, let's do the secretary position first. This must be a man. So how many men do we have? Well, we have 3. Now, once you have a man as secretary, all the other candidates, eliminating the one man that you've chosen, can be in the president's position. So, and it's not restricted. So how many individuals are left now? And the answer is 4. So 3 times 4 gives you 12. There are 12 possibilities if you were to make up that chart, and using a modification of our formula where we switch these offices around. We're electing the secretary first. So a problem-solving strategy, as they're suggesting in example 3, is whenever one or more parts of the task have special restrictions, try considering that part first, switching it around. All right, let's go on to example 4. Now, as we look at example 4, we're given counting 3-digit numbers with restrictions. How many non-repeating, odd, 3-digit counting numbers are there? Now, because of this restriction, odd 3-digit numbers, we have to look at in a 3-number system. Again, this wouldn't count as a 3 number because the 0 doesn't count. And this is an even number anyway. So if you had, let's say, 112, this wouldn't count because this is not an odd counting number. So the restriction is, what makes something an odd counting number? Well, its last digit has to be odd. And of our symbols, how many odd symbols are there? And there are 5. So we're using the restriction as our first item, and so we're limited to 5. Now, since they can't repeat, and we now can use a 0, well, I'm getting ahead of myself. we cannot use a 0 because this is actually the first digit here. We can't use a 0, and we can't use the odd number. So how many choices of our symbols are left? And the answer is 8. You can't use a 0. This is the first digit. And we cannot use the 5 that would repeat. Now, for the second digit, again, this is out of order. This is the odd values in the third place. This is now our first place. Can't use a 0, can't use the number that we already used. For our second place, now we can use a 0, but we can't use the previous two symbols, so this would also be 8. So multiplying this, using our formula, we get 320 counting. And again, this is written up here. You need to pause, study, and hopefully understand. This one's a little easier. So in counting license plate possibilities, we have, they're going to contain 3 letters, 3 digits. So how many license plates, numbers, and combinations are possible? Well, we don't have to write this one out. How many letters in our alphabet? 26 for the first. How many possibilities for the second? Because we're allowed repeats. 26. For the third, we're allowed 26. Now here we can use a 0, and there are 10 symbols in our number system. So 10 for the first, 10 for the second, 10 to the third, which gives us this. So again, there's more possibilities than people in the whole of the United States. So that's a pretty big number. Now in practice, they say a few of the possible sequences of letters are considered undesirable and aren't used. And you might say, well, what would that be? Well, again, the idea of a 0 and the letter O might be something you don't have. And then the letter S might be taken as a 5. That's what they're referring to here. Now, these are meant to be models as you get examples in your practice quiz me and homework to follow. And hopefully this is giving you a methodology, a strategy for doing them. So, you have a 4-digit number is to be constructed using only the digits 1, 2, and 3. How many such numbers are possible? Well, as we look at this, and this is going to be 4 digits here, now the numbers you have are 1, 2, and 3. Well, how many could go in the first digit? Well, there are 3 possibilities. How many in the second? Well, 3 possibilities there. And in the third, 3 possibilities. And in the fourth, 3 possibilities. So this is 3 to the fourth, which is 81. There are 81 possibilities. And this follows the fundamental counting principle. Now, how about if the number is less than 2,000? Only we have to look at this one. How many of these numbers are odd and less than 2,000? Well, in order for it to be, and let me set that up here. Now, in order for it to be less than 2,000, your first digit has to be a 1. So there's only one possibility for this first digit. Now, for the second two digits, or the second of the digits, there are 3 possibilities that you could put in there. And the same for this digit. But now, for it to be odd, there's only 2 choices for the last digit. And that's a 1 and a 3. So there's 2 choices. So multiplying all these, and again, we used our restriction, putting that first. This is going to be 9 times 2. This is going to be 18. Fooled you a little bit. And again, they have it there as well. Now, we did mention this already, that a problem-solving strategy is you look at what we've done here as your model to compare it to a similar problem. I guess the expression, you don't have to reinvent the wheel every time you want to have some transportation. The wheel is there, you may modify it, but we use what we know already for something similar. In example 7, we're distributing golf clubs. Vern has 4 antique golf clubs and wants to give to his 3 sons, Mark, Chris, and Scott. How many ways can the clubs be distributed? So for question 1, as we see here, how many ways can the clubs be distributed? And again, 4 antique clubs, 3 sons. Well, think of the number of clubs and how many could receive it. So the first club could be distributed 3 ways. The second club, 3 ways. The third club, 3 ways. The fourth club, 3 ways. So we end up with, as they show here, 3 to the 4th power, which is 81. Now in this next one, it gets a little more challenging. The power driver must go to Mark, and the number 3 wood must go to either Chris or Scott. So again, of the 4 drivers, of the 4 clubs, there's only one choice for the first one. But then now, there are 3 golf clubs left. So for the next choice, these 3 clubs could go to any of the boys. There's still 3 clubs left for the next choice and to any of the boys. But now one of these clubs and this original one has been taken out, so now there's only 2 clubs left, and that would be the distribution. And then 3 times 3 is 9 times 2 gives us 18. Now again, we're showing you these models so that as you get items similar to it, it gives you a strategy to solve. So after reading this example, they want 2 people to sit side by side. So a little diagram is helpful here. So if they sit in these 2 seats, or these two seats, or these two seats, they have the possibility of 3. And we can put that right there. Now, if they sit here, how many possibilities are left for the other two? Well, 2, to the right or the left. And then down below, again, to the right or the left. And there is our counting formula. 3 times 2 is 6 times 2. There is a total counting of 12 possibilities. We're now moving into a new term in our mathematics, which is called factorials. If we were to look at a sequence of possibilities, let's say the digits, non-repeating 3 digits using the digits 1, 2, and 3. Well, the first one would be you could use any of the 3. Then once you've used 1, you could use any of the 2 remaining. And then once you've used the second, you would have the 1 left. So we get the sequence 3, 2, 1, which when we multiply them together gives us a 6. Now, the products may be the total number of distinct arrangements of the 3 digits. And here now, similar to 4 objects, there are 4 in the first, 3, 1 that's less makes it 3, 2 that's less makes it 2, and then 1. So we get the sequence 4, 3, 2, 1, and if we multiply them together we get 24. Now, another way of referring to when we start with a high number and start going down like this is to say n factorial, where you say, for instance, 9, and the symbol for factorial is an exclamation mark. So 9 factorial simply means you're going to start with 9, then 8, 7, 6, 5, etc. to get, and then multiply them all together. Now in your calculators, usually somewhere there is access to this. So I know on the TI series you put 9 and then you go through math and go over a little bit, and I actually have a link up in the upper part here to show you how to do that. You can get an answer very quickly. So here are the factorials from 0 to 10. And again, this is in your textbook, and you don't have to memorize these, but you want to know what they stand for. So this is the formula. So you start off with n, then you subtract 1 from the n, and then 2 from the n, and then eventually it goes to 2, 1. Now, a problem-solving strategy is if they give you an example as a factorial, and it's 8 factorial, you can write the 8 and then go times 7 factorial. So for instance, if you had something like 10 factorial divided by 8 factorial, you could put the factors 10 times 9, then 8 factorial, because now what would happen to the 8 factorials? They would cancel out, and your answer is just this. Now if you put this into your calculator, if you can, that would work, Or this is a strategy for seeing a shortcut, in a sense, that you wouldn't even need your calculator. So here's some very, very good examples showing you how to work with factorials. So 3 factorial is 6. 6 factorial, showing you the process. Again, if you have a calculator that can do this operation, you get that directly. Now, for this one, you do the subtraction inside the parenthesis first and get 3 out of this. 3 factorial is 6. Now here, this is a little different. It's 720 from 6 factorial minus 6 from 3 factorial gives you 714. And then this technique that if you have 6 factorial divided by 3 factorial, you could write out the 6, 5, 4, then the 3 factorial. These would cancel out, and you would get 120. Now here you would actually do the division first and get a 2. 2 factorial is 2. Now when you get these humongous numbers like 15 factorial, they're putting it in scientific notation. If you put in 100 factorial, many calculators would not be able to do that. It's too large for most calculators. All right, and then a definition once again is the 0 factorial is just 1. So it's not 0, it's 1. Going on to arrangement of objects. When finding the total number of ways to arrange a given number of distinct objects, we can use factorials. The fundamental counting principle would do, it also does it, but factorials provide a shortcut. So the total number of different ways to arrange n distinct objects is n factorial. And again, we're showing you how to make things easier for yourself. Michelle has 7 essays to include in her English folder. In how many different orders can she arrange them? Well, you have the first one, 7 different ways. Then the next one, 6 different ways, 5 different ways. So it's just 7 factorial, which is this. Hard to imagine. Example 11, arranging preschoolers. She's taking 13 preschoolers to the park. How many ways can the children line up in single file to board the van? Well, initially there are 13 different ways. Then after that one is out, you have 12 different ways. And then that one's taken out and you have 11, and you go on down the line. This is 13 factorial, which is, wow. Again, the numbers are impressive. Now again, we're modifying the above and distinguishable arrangements. Here we do not want repeats or lookalikes. So notice we have how many letters in dad? Well, there are 3 letters, right? So what possible arrangements can you have? Well, you say 3 letters, it would be 3 factorial. But 2 of the letters are the same. So if you are cutting out repetitions, or as they describe here, lookalikes, we have to divide by the number of lookalikes, and that would be 2 factorial. So 3 factorial is 6, 2 factorial is 2, let me write it up here, 6 divided by 2 is going to be 3, and we've used, again, our factorials. Now a lot of this, believe it or not, is going to be tied in to our probability and predictability in future lessons. So here we're sort of laying the groundwork, looking at it one way. In the future lesson, we will see it being looked at another way. But we're going to use this. So this is very useful. So here is the rule. Arrangements of n objects containing lookalikes, that is, repeats. So the number of distinguishable arrangements of n objects where one or more subsets consist of lookalikes is given by this. So this would be the total characters or elements in a group, and then divided by their lookalikes. So let's take a look at, and again, these are models that you will follow. So how many letters? 1, 2, 3, 4, 5, 6, 7. So this will be 7 factorial. But how many repeats are there? Well, there's a 1, 2 for the A's, so 2 factorial. And for the T's, 1, 2, 3. 3 factorial. And that's how it's done. And if you put that in your calculator or figure out whatever method you're going to use to do the math, this is what you get. Now again, for letter B, there's 1, 2, 3, 4, 5, 6, 7, 8. This will be 8 factorial. And how many repeats? Well, the n is 1, 2 n's. So that would be 2 factorial. The G, 1, 2, 3. 3 factorial. And I guess we have 2 i's. 2 factorial. You might say, well, I didn't put it exactly this way. It doesn't make any difference. And again, this will give you this. Okay, so this wraps this up. It was sort of a long lesson, lots of stuff going on, but you will not develop mastery until you physically do your examples. And remember, what they want you to do here is to think about all of this.